Hey guys, in this video we're going to take a look at a few tricky trig definite integrals. So just as a reminder, there are always free guided notes available at dividingconquermath.com. So let's just jump right into it. So here are the 4 examples that I'm going to take a look at in this video, and they are very similar, and once you kind of learn the trick behind them, you'll actually realize that they're all quite interconnected. So ways you can use this video: you can either use this as a way to quiz yourself and see what you know, or if there's a specific example that you want to see, of course you can just fast forward to it. So let's get started. So for this first one, so this one maybe isn't so tricky, but it's just kind of knowing how to actually break it up, and this becomes kind of the foundation for a lot of other things that we're going to do. So in general, when you have an integral like this, it's kind of like a fraction that could be broken up. A lot of times, not always, but a lot of times, you're going to want to actually do that. So what I want to do is I want to break this into 1/2, and then we'll call this, how about 1/2 cosine of x? And so that's what I want to take the integral of, or that's what I want to integrate. Okay, so from here now I can just go ahead and take the antiderivative of this whole piece. So the antiderivative of this is 1/2 x plus 1/2 sine of x, but this is a definite integral, so I'm going to put square brackets around this, and I'm going to put my limits of integration here, right? So this is what I want to plug in now. So from here, now it's just a matter of plugging these pieces in and figuring out the rest of this. So this becomes pretty straightforward, I guess. So this will be 1/2 times pi over 4 plus 1/2 sine of pi over 4 minus 1/2 times 0 plus 1/2 sine of 0. So here's what I have to actually go through and evaluate now. And as you work through all of this, so this will come out to pi over 8 plus 2 times the square root of 2 over 8, or so I guess if you wanted to combine those into one fraction, you could do it like this. Or if you were just trying to come up with the decimal answer, this would come out to 0.7463 rounded, whichever way is an acceptable format for you to answer this. So that's kind of the idea. Okay, so now I want to move on to this next one, which looks almost identical, but there's just like a small piece in this that I wanted to throw out here. So having a number here is okay. So sometimes when people see a number here, like, so just to compare the difference, this was cosine of x and this one is cosine of 2x. Sometimes people forget that this is like, we have formulas for this. So I have just here for you, in case you need to write them down or review them, I have the antiderivative formulas for all of the trig functions. You might find this handy just to kind of reference. So this is basically telling you the structure of, if you have a number here, kind of how that antiderivative is going to look. So if you're having trouble kind of thinking through that, that's a really handy guide. So I will just go ahead and break this up again, and so let me do that real quick. Okay, so as far as taking the antiderivative of this, so this is not going to be too different from what we did before, so I'll go ahead and write that out first. Okay, so now you can kind of compare the difference between these. So because this 2 is here, I basically have to multiply now by this second factor of 1/2. So this is just slightly different from what we had before, but I wanted to just kind of draw out that comparison just so you could kind of see that. Sometimes people don't totally see that all the way, so it's helpful just to see the examples side by side. And so now once again we're just going to plug in everything, so let me go ahead and do that. Okay, so I've just finished this off because it was very similar to the last one, but I just wanted you to see what the final answer would be. So for these limits of integration, here's kind of all the work. So I plugged in pi over 3 and 0, so you can see that. Here's kind of what I came up with. So here's, if you need it in fractions, here's that answer, or if you need it as a decimal form, there's the decimal form. Okay, so that is actually just a really handy thing to kind of go through. So now we can start taking a look at some of the really tricky ones. Okay, so looking here at C, So this is sine squared x. And so again, going back to our list of antiderivative formulas, so we have antiderivative formulas for secant squared and cosecant squared, but we do not have anything for sine squared or cosine squared. That is not in our list. So just as a heads up, that this is like a really common thing that comes up with trig and integration. And so when that happens, then you basically know that you're going to have to now resort to using some other trig identity. Now, in this case, the handy identity is going to be the half angle identities. So again, maybe you want to pause the video just to write these down in case you're rusty on them. And you'll find that when you're working with a lot of trig and integrals, you'll want to have probably a list of identities just next to you if you're a little bit rusty. Okay, so that being said, this means that I really need to just restate this. So I'm going to use my half angle identity. So this will now be 1 minus cosine of 2x divided by 2 dx. And so now this goes back to exactly where we started the video, right? So in this case, this is minus. I think the previous example I had plus. So I'll just go ahead and sketch out the rest of the solution real quick for you. Okay, so there's my antiderivative, and now I'll just show you what everything looks like when you plug everything in. So in this case, just because of my limits of integration in this case, so here's what everything came out to. And if you compute all that, these are the pieces. So this will ultimately equal just pi over 4. So very similar to some of the last ones that we were looking at, but the trick here was the half angle identity. All right, so for our last example, so once again, we don't have some nice antiderivative formula that tells us what to do when this whole thing is being squared. And you really have to be quite literal about these formulas. So what that means is, since this is being squared, I'm just going to have to actually work it all out. So I'm going to have to multiply everything together. So let's go ahead and do that. So this is going to give me secant squared x plus 2 secant x cosine x plus cosine squared x. And so I'm still integrating all of this with respect to x. Now, one thing to notice with this, so we know that secant x is the same as 1 over cosine of x, and then so if I'm multiplying that against cosine, these two things actually drop out, so I'm just left with the 2. So I can restate this whole thing then as I need to integrate secant squared x plus 2 plus cosine squared x. So there you go. And so now we really kind of understand the tricks, and this is really common, by the way, with integration, especially like the higher you go up with integrals. So if I just thrown you at this problem, you might not have really known how to do this, but once you get the trick, like it all starts to really make a lot of sense. So you, like, a lot of this just comes down to practice and seeing the tricks over and over, and then eventually you kind of start getting good at kind of navigating some of these problems. So if you look at this and you just think, oh, I would have never had any idea, well, that's part of being a calculus student, and that's part of just, that's really common with learning. I was also, like, I struggled with this a lot at first too. So obviously, once again, we're gonna have to use our half angle identities for the cosine squared, but the rest of this I can go ahead and integrate. So let me just, let me go ahead and restate this one more time. So I'm gonna restate this last part, this cosine squared, using that half angle identity, and I'm just gonna go ahead and break up the fraction just right away. Okay, oops, and this should be 1/2. And if I wanted to maybe clean this up even more, I could combine these now if I wanted to. Let's see, well, I guess I could go ahead and do that. So 2 plus 1/2, so this will actually come out to 5 over 2, so there's kind of what everything will simplify to if you want to do that. If you didn't notice that, you can just plow ahead with this too. It's just an extra term. It doesn't really matter. Okay, so now if I take the antiderivative of this, this is going to be, so the antiderivative of secant squared is tangent, and then the antiderivative of 5 over 2 will be 5 over 2x. And then this last part, so we've already played around with this quite a bit, so this will be 1/4 sine of 2x. And so now I just have to finish evaluating all of this. And so what this is going to come out to then, So let's see, I'll plug in all of this. So I have tangent of pi over 4 plus 5 over 2 times pi over 4 plus 1/4 sine of, let's see, so 2 times pi over 4, this is ultimately going to become pi over 2. Okay, so I've got all of that. And then minus, so let's see, I might as well just plug in 0 into all of these pieces. So tangent of 0 is 0. This will be 0. So then if I plug 0 into this part, so sine of 0 is also 0. So this is all just going to be minus 0. And so then when you work all of this out, so ultimately what you're going to get is going to be, this will really come out to 5 over 4 plus 5 pi over 4. Oh, sorry, plus 5 pi over 8, my bad. 5 pi over 8. And if you're looking for a decimal, that'd be 3.2135. I'll just round up there. Okay, and so that would cover that particular example. So that's what I've got for you in this video. If you're looking for greater explanations of how things like the fundamental theorem of calculus works or other examples, I have plenty more, so feel free to check them out, and I'll see you guys next time.